Hi class, welcome to the Physical Behavior of Matter review. In this next test, we're going to look at the physical behavior of matter. We're going to focus on the three principal phases of matter: solids, liquids, gases, and solutions, mixtures. For solids, we're going to be concerned with the basic characteristics of solids and how bond type influences the characteristics of solids. For liquids, we're going to focus on the basic characteristics of liquids and how vapor pressure and intermolecular forces play a role in the properties of liquids. For gases, we're going to look at real versus ideal gases as described by the kinetic molecular theory. From there, we're going to apply the principles of the combined gas law. And also look at the relationship of the number of particles of gas under specific conditions. Now, for solutions, we're going to look at what is a solution, going to concern ourselves with solubility as described with reference table F. We're also going to look at solubility in terms of concentration on reference table G, looking at saturated, unsaturated, and supersaturated. Solution will also look at trends of solubility of solids and gases in aqueous solutions. Solubility will also look at calculating concentration, and concentration is calculated in molarity, parts per million, and percent composition. Finally, in solutions, we'll look at why certain substances dissolve and basically explore the like dissolves like concept. Some of the ideas on the physical behavior of matter review sheet are very important in discussing the physical behavior of matter, but they've been tested in earlier portions of the course, and so that we can test your true understanding of the most recent content may not be tested on your upcoming exam. A fantastic place for review will be your High Marks book. I recommend you examine High Marks Chapter 1B and High Marks Chapter 6. I will post an image of the multiple choice answers in the next slide. Here are the work and answers to my High Marks Chapter 1B questions. Notice it's very important that you underline key terms and refer to your reference table. The questions involving vapor pressure, you can refer to reference table H. There are some important things to note here on reference table H. Table H gives the vapor pressure of 4 different liquids. You can notice that as the temperature increases, the vapor pressure of the liquid increases. So we know that as temperature increases, liquids tend to evaporate more quickly. Also recall that the normal boiling point correlates with the intersection of any given line with the vapor pressure of normal or standard pressure, which is 101.3 kilopascals. So for propanone, the normal boiling point occurs here at this intersection. So you will have to just read the graph down to see what the normal boiling point is. Please also note that on the x-axis, the scale is by 5s, but on the y-axis, the scale is by 10s. So the normal boiling point of propanone is approximately 55 degrees Celsius. The last big idea to look here is that when liquids evaporate very easily, they are not held together by strong intermolecular forces. Or liquids that do not easily evaporate, they are held together by strong intermolecular forces. Therefore, the stronger the intermolecular force, the lower the vapor pressure. This means the more intermolecular forces a substance has, the more it will resist evaporating. Recall that if we believe the assumptions of the kinetic molecular theory, which are that gases are in constant random straight line motion, gas particles have no real volume because they are so far apart. Gas particles have perfectly elastic collisions, which means they do not gain or lose energy upon colliding. And gas particles have no intermolecular forces, so their movement is not hindered by the presence of other gas particles. If we believe these four things about gases, all of which are not exactly true, then we can present math to just predict the behavior of gases under conditions. Now, the behavior of gases is best described with the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. This is found on reference table T as in Tom. Recall that there are a subset of 3 gas laws that can be described using the combined gas law. So whenever a variable is constant, it can simply be removed. For instance, at constant temperature, if we remove temperature, we're left with P1 V1 equals P2 V2. This is called Boyle's law. Or at constant pressure, we are left with V1 over T1 equals V2 over T2. Notice I just removed the pressure variable because pressure was constant. This is called Charles' law. And lastly, Gay-Lussac's law is at constant volume. In all of these formulas, it's very important that you remember that the temperature must be Kelvin. Like in question number 10 on the high marks homework, you will be responsible to know the general graph of the relationship between two variables. Basically, we know that the graph for Boyle's law looks something like this, and the graph for both Gay-Lussac's and Charles' law have a direct relationship. So again, it is important that you commit to memory the ideas of the kinetic molecular theory and how it describes ideal gases. You should also know that real gases are different than ideal gases. You should be able to use the combined gas law, all of its permutations, and be able to graph the relationship between any two variables in the combined gas law. Lastly, you should understand under what conditions real gases behave most ideally. So recall that real gases behave most ideally under conditions that are similar to summer, because summer is ideal or perfect because of the high temperatures and the low pressure to do schoolwork. Also, the most ideal gases, or the happy gases, include hydrogen and helium gas, because those are the two smallest gaseous atoms on the periodic table. The final big idea you're going to need to remember for gases is Avogadro's law, which states that gases under the same conditions of pressure, temperature, and volume, the conditions described in the combined gas law, will always have the same number of particles. This is because gas particles have no real volume, so they all have the same volume. Remember that Avogadro goes on to describe that 1 mole of gas at standard temperature and pressure should contain 22.4 liters of any gas, regardless of the formula. So here we can see this big idea on our homework. You can also remember that there are 22.4 liters of any gas at STP.